The Untangled Codebase, building resilient software with clean, onion, and hexagonal architecture. Chapter 1, The Tangled Web We Weave, Why Architecture Matters. Imagine a house. Not just any house, but one that started as a small, cozy dwelling. Over time, new family members arrived, and space became scarce. So, new rooms were added, seemingly wherever a free patch of land appeared. A bathroom here, a kitchen there, perhaps a new bedroom extending into the garden. There was no master plan, just immediate needs driving construction. Over the years, the house grew into a sprawling, labyrinthine structure. Pipes zigged and zagged in illogical paths, electrical wires crossed behind walls in a dangerous tangle, and adding a simple window became an arduous task, risking the structural integrity of the entire building. This house, chaotic and unpredictable, is a metaphor for countless software systems in existence today. Just as a poorly planned house becomes a maintenance nightmare and a safety hazard, a poorly architected code base can cripple an organization, stifle innovation, and turn simple feature additions into Herculean efforts. In the fast-paced world of technology, the pressure to deliver features quickly is immense. Deadlines loom, user demands evolve, and competitors are always just around the corner. In this rush, it's easy to dismiss architectural design as a luxury, a nice-to-have that can be deferred until later. The mindset often becomes, let's just make it work, and we'll fix the messy parts later. The problem, as many seasoned developers and business leaders have painfully learned, is that later often never comes, or when it does, the fixing requires a complete demolition and rebuild. The big ball of mud, software's common scourge. One of the most infamous anti-patterns in software development is the big ball of mud. This describes a system characterized by an absence of discernible architecture, where everything is connected to everything else in an ad hoc, spaghetti-like fashion. Components with wildly different responsibilities are intertwined. Business logic is mixed with database access code, and user interface elements directly manipulate data, bypassing any semblance of organized flow. In a big ball of mud, changes are risky. A seemingly small change in one part of the system can cause unexpected failures in completely unrelated areas. Developers spend more time fearing what they might break than confidently delivering new value. Maintenance is a nightmare. Understanding how the system works requires a massive cognitive load. New team members struggle to grasp the entangled logic, leading to a steep and frustrating learning curve. Finding the root cause of a bug becomes an archaeological expedition. Deployment is fragile. Because everything is tightly coupled, deploying one small fix often necessitates deploying the entire application, introducing more risk and downtime. Testing is an afterthought or impossible. Due to the lack of clear boundaries and dependencies, isolating parts of the system for automated testing becomes incredibly difficult, if not impossible. This leads to manual, time-consuming, and often incomplete testing cycles. Scalability is a pipe dream. When distinct parts of the system cannot be independently scaled, adding more resources to handle increased load often means scaling up everything, leading to inefficient resource utilization and higher costs. Team productivity plummets. Developers spend increasingly more time managing complexity rather than building features. Morale drops, and the once exciting project becomes a source of dread. The cost of a neglected architecture isn't just about technical debt. It's about business agility. A tangled code base slows down feature delivery, increases time to market, and makes it harder to respond to competitive pressures or new market opportunities. It's a hidden tax on innovation and growth. What is architectural design and why is it crucial? Architectural design, at its heart, is about making fundamental choices regarding how a software system will be structured, how its components will interact, and how it will meet its non-functional requirements, e.g., performance, security, scalability, maintainability, testability. It's the blueprint, the master plan for the house we build. Good architectural design aims to manage complexity, break down a large, daunting problem into smaller, manageable, and understandable pieces. Enable change. Design the system in such a way that it can evolve and adapt to new requirements without massive refactoring efforts. This is perhaps its most crucial role. Promote testability. ensure that individual components and key business logic can be easily isolated and tested, leading to higher quality and fewer bugs. Facilitate collaboration. Provide clear boundaries and responsibilities, allowing different teams or individuals to work on separate parts of the system with minimal interference. Improve performance and scalability. Lay the groundwork for efficient resource utilization and the ability to handle increased load gracefully. Increase maintainability. Make the system easier to understand, debug, and enhance over its lifespan. Neglecting architecture isn't saving time. It's borrowing time from the future with exorbitant interest. The initial velocity gained by ignoring design patterns is quickly lost as the system becomes brittle and difficult to work with. This book will introduce you to 3 powerful architectural patterns: hexagonal architecture, onion architecture, and clean architecture, that stand as antidotes to the big ball of mud. They offer systematic approaches to building resilient, maintainable, and testable software systems. They all share a common philosophy: protect the core business logic from the fickle nature of external technologies. By understanding their principles, differences, and practical applications, you will gain the clarity and tools to untangle your codebases and build software that stands the test of time. Let's begin by exploring the foundational principles that allow these architectures to deliver on their promise of flexibility and robustness. Chapter 2: Foundations of Flexibility. Core Principles of Robust Design. Before diving into the specifics of hexagonal, onion, and clean architectures, it's essential to understand the bedrock principles upon which they are all built. These aren't just abstract academic concepts. They are practical guidelines that, when applied, lead to software that is easier to manage, test, and evolve. Think of them as the fundamental rules of good construction that ensure our metaphorical house is structurally sound, regardless of its eventual style or number of rooms. Separation of concerns. One responsibility, one place. At the very heart of all good software design is the principle of separation of concerns. It's deceptively simple. Each part of a system should have only one reason to change, and that responsibility should be encapsulated within its own logical unit. Imagine a modern restaurant. The chef's concern is cooking. The waitstaff's concern is serving. The cashier's concern is handling payments. If the chef suddenly had to take orders, serve tables, and collect money, efficiency would plummet, mistakes would multiply, and the whole operation would grind to a halt. Each role has a distinct concern or responsibility, operating independently while contributing to the overall goal. In software, this means business logic. Code that defines what the application does in terms of its domain, e.g., how to calculate a loan, how to process an order. Data access. Code that deals with how data is stored and retrieved, e.g., interacting with a database, calling an external API for data. User interface. Code that handles how information is presented to and received from the user, e.g., web pages, mobile screens. External integrations. Code that communicates with third-party services or external systems. When these different concerns are mixed, for instance, if your code that calculates loan interest also contains commands to save data to a specific SQL database, or if your user interface directly interacts with the database, you create a God object or a tightly coupled system. A change in the database schema, a new user interface requirement, or an update to the loan calculation algorithm would force you to modify a single, large piece of code, increasing the risk of introducing bugs. Separating concerns allows us to update the user interface without touching the business logic, change the database technology without affecting the core application, and evolve business rules independently of how data is stored. This is the first crucial step towards building flexible and maintainable systems. Inversion of control, IOC, and dependency injection. Don't call us, we'll call you. Once we separate concerns, we need a way for them to interact without becoming tightly intertwined. This is where inversion of control, IOC, comes in. IOC is a broad design principle where the flow of control of a program is inverted. Instead of manually creating and managing an object's dependencies, the other objects it needs to function, the object declares its dependencies, and a framework or container injects them at runtime. Consider building a custom car. Without IOC, you, as the car builder, would be responsible for making every part from scratch, machining the engine block, forging the gears, wiring every circuit. With IOC, you specify what kind of engine, what kind of tires, and what kind of steering wheel you need, and a specialized factory. An IOC container provides those components, allowing you to focus on the car's overall assembly and function. The most common implementation of IOC in modern software is dependency injection, DI. Instead of a class explicitly creating its dependencies, those dependencies are provided to it, typically through its constructor, a method, or a property. For example, if you have a user service that needs to save user data, instead of the user service directly creating a database repository like this. Without dependency injection, bad. You have a user service class that creates its own dependency, database repository, internally. This makes the user service directly coupled to that specific type of database repository. With dependency injection, good. In this approach, the user service declares that it needs a user repository by having it passed into its constructor. The user repository itself would be an abstraction, an interface, allowing different concrete implementations to be plugged in without changing the user service. The user repository in this example would typically be an interface, an abstraction, and the concrete implementation, e.g., SQL user repository, Mongo user repository, would be provided by an external mechanism. This is vital for flexibility because testability. You can easily inject a mock or fake repository for testing the user service in isolation without needing a real database. Flexibility. You can swap out the database technology, e.g., move from SQL to NoSQL, by simply providing a different user repository implementation without changing the user service itself. Reduced coupling. Components are loosely coupled because they don't depend on concrete implementations, but rather on abstractions. IOC and DI are fundamental enablers for the architectural patterns we will discuss, allowing them to truly decouple different layers and responsibilities. The dependency rule, the North Star of clean architecture. If separation of concerns is about dividing responsibilities, and IOC is about managing how those responsibilities interact, then the dependency rule defines how those interactions should be structured. It's the most critical principle underpinning all the discussed architectures. The dependency rule states that source code dependencies can only point inward. Imagine a set of concentric circles. The innermost circle represents your core business logic, the most stable and abstract part of your application. As you move outwards, each circle represents components that are more concrete, less abstract, and more subject to change, e.g., user interfaces, databases, web frameworks. The dependency rule dictates that code in an outer circle can know about and depend on code in an inner circle. However, code in an inner circle must never know about or depend on code in an outer circle. An outer circle component, like a web controller, can call an inner circle component, like a create user business logic service. But the inner circle component must have no knowledge of the web controller or the web framework it's using. Why is this so important? Protection of business rules. The innermost circle contains your unchanging business rules. By making it independent of everything else, these rules remain stable and unaffected by changes in UI, database, or external tools. They are the least volatile part of your system. Testability. Since the core business logic has no external dependencies, it can be unit tested in complete isolation without needing a database, web server, or any other external system. Framework independence. Your core application doesn't care if you're using a specific web framework or a particular database. This means you can swap these out relatively easily, protecting your investment in your business logic. Portability. The application's core can be reused in different contexts, perhaps a web application, a command line tool, or a mobile app, all using the same core business logic. This rule is enforced by interfaces, abstractions. An inner circle might define an interface that an outer circle implements. For example, a user creation, business logic inner circle might need to save data. It defines an user repository interface. A concrete SQL user repository, outer circle component, would implement that interface and handle the actual database interaction. The business logic only depends on the interface, not the concrete SQL implementation, thus adhering to the dependency rule. Solid principles, architectural implications. While solid principles are often discussed at the class design level, their implications extend significantly to architectural design, particularly the dependency inversion principle, DIP, single responsibility principle, SRP. This translates to separating concerns at an architectural level. A layer or module should have a single reason to change. The UI layer changes when UI requirements change. The data access layer changes when data needs to be stored differently. Open-closed principle OCP. Software entities should be open for extension, but closed for modification. A well-designed architecture allows you to add new features or technologies by adding new code, extending, rather than changing existing working code, modifying. This is achieved through abstractions and adherence to the dependency rule. Dependency inversion principle, DIP. This is perhaps the most crucial solid principle for architecture, directly supporting the dependency rule. It states, high-level modules should not depend on low-level modules. Both should depend on abstractions. Abstractions should not depend on details. Details should depend on abstractions. In simpler terms, instead of your business logic high-level module directly depending on a specific database implementation, low-level module, both should depend on an interface abstraction. The concrete database implementation then depends on and implements that interface. This inverts the natural dependency flow and is the mechanism by which the dependency rule is made possible. Understanding these foundational principles, separation of concerns, inversion of control, especially dependency injection, the dependency rule, and the architectural implications of solid, particularly DIP, will equip you to grasp the elegance and power of hexagonal, onion, and clean architectures. They are not just patterns. They are systematic applications of these core principles to build software that is robust, adaptable, and a joy to work with. With these foundations firmly in place, let's now explore the first concrete architectural style, hexagonal architecture with its intuitive ports and adapters approach. Chapter 3, Hexagonal Architecture, Ports and Adapters to the Rescue. In Chapter 1, we lamented the big ball of mud and the chaos it brings. In Chapter 2, we laid the groundwork with core principles like separation of concerns, inversion of control, and the all-important dependency rule. Now, it's time to introduce our first concrete architectural solution, one that beautifully embodies these principles. Hexagonal architecture. Coined by Alistair Cockburn in 2005, hexagonal architecture is also famously known as ports and adapters architecture. Its core intent is elegantly simple: to cleanly separate the application's core business logic from its external interactions. In essence, it aims to protect your precious domain code from the fickle changes of user interfaces, databases, external services, or any other infrastructure details. The core idea, inside versus outside. Imagine a regular polygon with 6 sides, a hexagon. This hexagon represents your application core, sometimes called the domain, business logic, or application logic. This is the heart of your software, containing the unique rules, processes, and data structures that define what your application truly does. It's the stable, unchanging essence of your system. Everything else, the user interface you click on, the database that stores information, the external payment gateway, the logging system, lives outside this hexagon. These are all external components, prone to change, often dictated by technological trends or third-party decisions. The insight of hexagonal architecture is that your core application should not know or care how it's being used or how its data is stored. It should simply focus on its primary mission, executing business rules. Ports, the contractual gateways. How does your independent hexagon communicate with the outside world without knowing its specifics? Through ports. Think of ports as clearly defined openings or sockets on the sides of your hexagon. They are abstract interfaces, simply describing what the application core needs to do or what it can do. They specify a contract, a set of operations or functions that the application core either provides or requires. For instance, your application core might need to save user data. Instead of directly knowing about a SQL database, it defines a port called User Repository Port that simply says, I need to be able to save a user and retrieve a user. It doesn't specify how this will happen, only that it needs to happen. Similarly, if an external system wants to use your application core, e.g., a user interface wants to request a report, the core will expose a reporting service port that defines the operations to generate a report. Crucially, ports are technology agnostic. They are pure abstractions found within your application core, expressed in terms of your business domain, not database queries or web requests. Adapters, the translators and connectors. If ports are the sockets, then adapters are the plugs. An adapter is a piece of code that implements a port. Its job is to translate the specific technology of the outside world into a form that the application core can understand, and vice versa. Adapters live outside the hexagon and know about the specific technologies they interact with. Let's revisit our user repository port. You might have an SQL database adapter that implements this port. This adapter knows how to take a user object from the core, translate it into a SQL insert statement, and send it to your PostgreSQL database. If you later decide to switch to a NoSQL database like MongoDB, you would simply create a MongoDB adapter that also implements the user repository port, without touching your core business logic at all. This is the power of hexagonal architecture. The core remains pristine and stable, completely decoupled from the ever-changing infrastructure. Two kinds of adapters, driving and driven. Within hexagonal architecture, adapters typically fall into two categories, based on who initiates the interaction. Primary or driving adapters. These adapters initiate calls into the application core. They drive the application. They respond to external stimuli and tell the core what to do. Examples: a web API adapter, like a REST controller, that receives an HTTP request and calls a create user operation on a port exposed by the application core. A graphical user interface, GUI adapter that translates button clicks into commands for the core. A command line interface, CLI, adapter that parses command line arguments and invokes core functionalities. An automated test adapter that simulates user input to test the core independently. Secondary or driven adapters. These adapters are called by the application core. The core drives them to fulfill its internal needs. They provide services that the core requires. Examples: a database adapter, like our SQL database adapter, that implements the user repository port to save and retrieve data from a database. An email service adapter that implements a notification port to send emails through a third-party email provider. A payment gateway adapter that implements a payment processing port to interact with a service like Stripe or PayPal. A logging adapter that implements a logging port to write messages to a file or a logging service. How it all connects. The flow works like this. A driving adapter, e.g., a web controller, receives an external request. It translates this request into a format understood by a port on the application core. The application core performs its business logic. If the core needs to interact with an external component, e.g., save data, send a notification, it calls out to a port that defines the required service. A driven adapter, e.g., a database adapter, implements this port, translating the core's request into the specific actions needed for the external system. The result of the driven adapter's operation, e.g., successful data save, is returned to the core, then passed back up through the driving adapter to the external requester. This setup ensures that the dependencies always point inward. Adapters depend on the ports they implement, and ports are defined by the core. The core knows nothing of the outside world, adhering perfectly to the dependency rule we discussed. The benefits of the hexagon. The ports and adapters metaphor isn't just about aesthetics. It delivers significant practical advantages. Improved testability. Because the entire application core is isolated from external concerns, you can test it comprehensively and rapidly using automated tests. You simply write a driving adapter test that calls the core's exposed ports and injects driven adapter test stubs, simple fake implementations for any external services. No need for a running database or web server. Framework and technology independence. Your core application is blissfully unaware of whether it's accessed via a web framework, a desktop application, or a message queue. Similarly, it doesn't care if you're using a relational database, a NoSQL database, or even an in-memory data store. This allows you to swap out frameworks or databases as technology evolves or business needs change, with minimal impact on your most valuable code. Enhanced maintainability and evolution. With clear boundaries, developers can work on specific parts of the system without inadvertently affecting others. New features requiring new external integrations simply mean creating new adapters, not refactoring the core. Increased system longevity. The stable, well-tested core business logic becomes a durable asset, capable of outliving the user interfaces and databases it interacts with. Better communication. The explicit definition of ports forces clarity about the application's boundaries and its interactions with the outside world, improving communication within development teams. Hexagonal architecture is a powerful way to implement separation of concerns and enforce the dependency rule through dependency inversion. It's about drawing a strong, unyielding boundary around your core business logic, ensuring it remains clean, testable, and adaptable, regardless of the turbulent technological landscape surrounding it. With hexagonal architecture, your software gains remarkable resilience. But it's not the only strategy. Next, we'll explore onion architecture, which similarly emphasizes the domain, but with a slightly different layered concentric structure. Chapter 4, Onion Architecture, Prioritizing the Domain Core. In the previous chapter, we explored hexagonal architecture, a powerful approach to isolating your application's core logic from external concerns using the ports and adapters metaphor. Now, let's turn our attention to a closely related architectural style that shares many of hexagonal's goals but presents them through a slightly different lens. Onion architecture. Introduced by Jeffrey Palermo in 2008, onion architecture is aptly named for its structure, a series of concentric layers that resemble an onion. Each layer wraps around the inner ones, and critically, dependencies always flow inward. This central principle ensures that the most important part of your application, your business domain, remains at the core, independent of accidental complexity introduced by infrastructure, user interfaces, or frameworks. The core idea, domain at the center. Like hexagonal architecture, onion architecture starts with the fundamental premise that your application's core business logic, the domain model, is the most valuable and stable part of your software. This core should be unburdened by concerns about databases, web frameworks, or operating systems. It should be pure, focused solely on the rules and entities that define your business. The onion architecture explicitly structures the application to ensure this domain centricity. It places the domain model at the very heart of the application, around which other layers are built. The layers of the onion. While precise naming and number of layers can vary slightly depending on the interpretation, a typical onion architecture consists of at least 4 primary layers. The domain model, innermost layer. This is the pure heart of your application. It contains the fundamental business entities, value objects, and domain rules. It should have no dependencies on any other layer. It contains plain, old business objects that define what your business process is about. Think of it as the raw business logic, completely free from concerns about how it's stored, displayed, or integrated. Domain services layer. Immediately surrounding the domain model, this layer contains business logic that orchestrates operations involving multiple domain entities or that cannot naturally fit within a single entity. It depends only on the domain model. Examples include services for complex calculations, cross-entity rules, or processes that require external validation from abstractions defined in this layer. Application services layer. This layer contains the application-specific use cases. It defines what the application does in terms of its features. It orchestrates the flow of data to and from the domain services and the domain model layers. It also defines interfaces, abstractions for actions that require external infrastructure, such as persistence interfaces or notification interfaces. This layer depends on the domain services and domain model layers. It has no dependency on the outermost infrastructure layer. Infrastructure layer, outermost layer. This is where all the concrete implementations live. It contains the details of how things are done. This includes database repositories, implementing persistence interfaces defined in application services, UI components like web controllers, external API clients, logging services, and framework-specific code. Crucially, the infrastructure layer depends only on interfaces or abstractions defined in the inner layers. It knows about the database, but the inner layers only know about a generic repository interface. This is the embodiment of the dependency rule, the strict dependency rule in action. The defining characteristic of onion architecture is its unwavering adherence to the dependency rule. Outer layers can depend on inner layers, but inner layers can never depend on outer layers. Let's trace a typical interaction. A request comes in, e.g., from a web UI in the infrastructure layer. A component in the infrastructure layer, e.g., a controller, receives the request. The infrastructure component calls an application service in the application services layer to handle the request. The application service orchestrates the business logic, potentially interacting with domain services and domain models in their respective inner layers. If the application service needs to save data, it calls a method on an interface defined within the application service layer, e.g., iUserRepositorySaveUser. A concrete implementation of iUserRepository resides in the infrastructure layer, e.g., SQL User Repository. This infrastructure component depends on the iUserRepository interface, thus adhering to the dependency rule by pointing inwards. The infrastructure component performs the actual database operation. The result flows back through the layers, eventually returned by the infrastructure component to the initial requester. This architecture fundamentally inverts the typical way we often structure applications, where the business logic easily becomes entangled with database access or UI details. Palermo argues that the application builds inward toward the domain model, not outward from the data access. The benefits of the onion. The concentric, dependency-inverting structure of onion architecture yields significant advantages, many of which overlap with those of hexagonal architecture due to their shared underlying principles. Domain independence, the most significant benefit. Your core business rules are truly isolated. They don't know about databases, web servers, or any other external concerns. This makes them highly stable and reusable. Enhanced testability. Individual layers, especially the inner domain and application services, can be tested in complete isolation. You can unit test your business logic without spinning up a database or a web server, making your test suites fast and reliable. Framework agnostic core. Your application's core logic is not tied to any particular framework, e.g., a specific web framework or ORM. You can swap out these technologies with relative ease, protecting your development investment. Increased maintainability and evolution. Changes in external details, like switching databases, affect only the outermost infrastructure layer, minimizing ripple effects across the entire system. New features often mean adding new use cases in the application services layer, extending the system rather than modifying existing core components. Clarity and separation of concerns. Each layer has a distinct responsibility, making the code base easier to understand, navigate, and manage for development teams. Onion versus hexagonal, a glimpse forward. While both hexagonal and onion architectures aim to decouple the domain from infrastructure, their primary difference lies in their conceptual model. Hexagonal architecture emphasizes ports on the sides of a core, representing entry-exit points for interaction with external adapters. Onion architecture emphasizes strictly enforced concentric layers, with the domain at the very center and dependencies always flowing inward through these layers. Think of it this way. Hexagonal is like a device with specific ports you can plug adapters into. Onion is more like a strict stratification of concerns, with the most important and stable parts buried deep within, protected by outer, more volatile layers. These conceptual differences can influence how you structure your code and enforce boundaries. We'll delve deeper into their similarities and nuances in a later chapter. For now, understand that onion architecture provides a compelling, layered approach to safeguarding your domain model, promoting testability, and building software that is flexible and resilient to change. It's another powerful tool in the architect's arsenal for untangling complex code bases. Chapter 5, Clean Architecture, the Unified Vision. We've explored hexagonal architecture with its ports and adapters, isolating the core business logic from external interactions. We then delved into onion architecture, which enforces a strict concentric layering with the domain at its heart, ensuring dependencies flow inward. Now, we arrive at the culmination of these ideas, clean architecture. Introduced by Robert C. Martin, affectionately known as Uncle Bob, clean architecture is not an entirely new architectural pattern, but rather a synthesis, a powerful unification of the best principles found in these other approaches and older layered architectures. It's a pragmatic and holistic guide for structuring software applications to achieve maximum independence, testability, and maintainability. Uncle Bob famously articulated clean architecture as a set of rules for arranging software that result in systems which are independent of frameworks. Your business rules should not rely on the existence of any particular software library. Testable. The business rules can be tested without the UI, database, web server, or any other external element. Independent of UI, you can change the user interface easily without changing the rest of the system. Independent of database, you can swap out your database, SQL, NoSQL, etc., without affecting your business rules. Independent of any external agency, your business rules simply don't know about the outside world. The core idea: concentric circles with the dependency rule. Clean architecture visualizes the system as a set of concentric circles, similar to onion architecture. The most crucial rule governing these circles is, again, the dependency rule. Source code dependencies can only point inward. Code in an inner circle must not know anything about code in an outer circle. When you reference something in an outer circle from an inner circle, you are breaking the dependency rule and thus violating clean architecture. Let's break down the typical 4 primary circles, from innermost to outermost. Entities. What it contains: the innermost circle houses your enterprise business rules. These are the most general and highest level rules. They encapsulate the fundamental data structures and critical business rules that are independent of any specific application. They are so general they could potentially be used across many different applications within an enterprise. Dependencies. They have no dependencies on anything. They are pure plain old objects, POJOs, POCOs, or similar, free from any framework or database concerns. Example: a user entity with properties like name, email, and methods like validate email, or an order entity with rules governing its status and total calculation. Use cases, interactors. What it contains: this circle contains the application business rules. These rules are specific to the particular application being built and orchestrate the flow of data to and from the entities. They define how the application works to fulfill a specific user interaction or system event. Dependencies. They depend only on the entity's circle. They know nothing about the UI, database, or web framework. Example: a create user use case that takes user input, validates it against business rules, possibly using the user entity, and then instructs an user repository interface, defined in this use case layer, to save the user. A process order use case that interacts with order entities to transition their state. Interface adapters. What it contains: this layer is a set of adapters that convert data from the format most convenient for the use cases and entities to the format most convenient for the external frameworks and devices. It acts as the boundary. This includes presenters, prepare data for the UI; controllers, receive input from the UI and translate it into a format suitable for the use cases; gateways, repositories. These are the concrete implementations for database access or external API calls. They implement interfaces defined in the use cases layer. Dependencies can depend on use cases and entities. It implements interfaces defined in inner layers. Example: a user controller receives HTTP request, extracts data, calls create user use case. A user presenter takes data from create user use case and formats it for JSON response. A SQL user repository implements the user repository interface defined in Create User Use Case, and talks to the SQL database. Frameworks and drivers, what it contains. The outermost layer is composed of frameworks and tools, such as the web framework, the database, general-purpose libraries, and any other external components. This is where most of the infrastructure resides. Dependencies. It depends on everything else. It glues together the application and provides the concrete implementations for the abstractions defined by the inner layers. Example: an ASP.NET Core web application, a Spring Boot application, an Oracle database, an Elasticsearch instance. These are the details, and clean architecture ensures your application can exist without strong ties to them. The flow of control and its inversion. Let's trace a typical user request in a clean architecture system. A user interacts with the UI, e.g., a web form, which is part of the frameworks and drivers layer. The UI dispatches this interaction to a controller in the interface adapters layer. The controller translates the UI-specific request data into a standard data structure, often called a request model, or DTO, that the use case understands. The controller then calls the appropriate use case in the use cases layer, passing it the request model. The use case performs the application-specific business logic. If it needs to interact with a database or external service, it invokes an interface, e.g., user repository, that it defined in its own layer. The concrete implementation of that interface, e.g., SQL user repository, is located in the interface adapters layer. This implementation actually communicates with the database in the frameworks and drivers layer. This is where dependency inversion is critically at play. The use case depends on an interface, and the concrete implementation depends on that same interface, effectively inverting the normal flow of control. The use case updates the entities as needed. Once the use case finishes its work, it prepares a response model or output port data structure for the presenter in the interface adapters layer. The presenter takes this response model and formats it for the UI, e.g., converting it to JSON or HTML. 10. The formatted data is sent back to the UI in the frameworks and drivers layer, which then displays it to the user. This circuitous path might seem complex at first, but it is precisely this careful dance of dependencies and abstractions that provides the immense benefits. Benefits of the clean architecture. Clean architecture, by combining the strengths of its predecessors and emphasizing rigorous adherence to the dependency rule, offers the highest degree of architectural isolation and flexibility. Maximum independence. Your business logic is truly independent of databases, UI, third-party frameworks, and external services. This means decisions about these external components can be delayed or easily changed without ripping apart your core system. Ultimate testability. The innermost layers, entities, and use cases contain your most important code and are free of external dependencies. This makes them incredibly easy and fast to unit test in isolation, leading to a highly reliable and maintainable core. Maintainability and scalability. With clear boundaries and well-defined responsibilities, teams can work on different parts of the system concurrently. Changes in one area, e.g., switching database vendors, are localized, minimizing disruption. New features often mean adding new use cases rather than modifying existing ones, allowing the system to grow gracefully. Portability. The core business rules can be easily deployed in different environments or serve different client applications, web, mobile, desktop, console app, without modification. Enforced separation of concerns. This architecture practically compels developers to put code in its proper place, preventing the big ball of mud and fostering a well-organized codebase. Clean architecture is demanding in its discipline, but the long-term rewards in terms of system longevity, adaptability, and developer productivity are substantial. It provides a robust framework for building systems that can withstand the test of time and the inevitable winds of technological change. Now that we've explored each architectural style individually, it's time to put them side by side. In the next chapter, we'll unpack their similarities and unveil their subtle but important nuances, helping you understand when and why you might choose one over another, or how they blend together. Chapter 6. Unpacking the similarities, unveiling the nuances. a comparative analysis. We've now explored hexagonal, onion, and clean architectures individually, dissecting their structure, principles, and benefits. By this point, you might have noticed a considerable overlap in their goals and fundamental mechanisms. Indeed, a common question among developers is, are they just different names for the same thing? The answer is both yes and no. They are deeply related, like members of the same family, sharing core DNA, but with distinct personalities and emphases. This chapter aims to clarify their relationships, highlight their common ground, and then delve into the subtle but important nuances that differentiate them. The grand unifying principles, what they all share. Despite their different diagrams and terminologies, hexagonal, onion, and clean architectures are all manifestations of the same fundamental architectural philosophy. Their shared DNA includes domain centricity. At their absolute core, all three architectures prioritize the business logic or domain model. This core is considered the most important and stable part of the application, and everything else is seen as infrastructure or a delivery mechanism that supports this core. In hexagonal, it's the hexagon itself. In onion, it's the innermost domain model layer. In clean, it's the entities and use cases circles, isolation from volatile dependencies. All three patterns strive to isolate the core business logic from external factors that are prone to change. These include user interfaces, UI, web, mobile, desktop, console, databases, SQL, NoSQL file systems, frameworks, Spring, ASP.NET, Django, React, external services, payment gateways, email providers, logging systems. The goal is to prevent these details from polluting or dictating the design of the core business rules. Strict adherence to the dependency rule. This is arguably the most critical shared principle. In all three architectures, dependencies flow inward. Inner layers or components cannot know about or depend on outer layers or components. This is achieved through dependency inversion, where inner components define interfaces and outer components implement those interfaces. Hexagonal, adapters implement ports, interfaces defined by the core. Onion, outer layers depend on interfaces provided by inner layers. Clean, outer circles depend on abstractions defined by inner circles. High testability of core logic. A direct consequence of isolation and the dependency rule is that the core business logic becomes exceptionally easy to test. Since it has no hard dependencies on frameworks, databases, or UI, it can be unit tested in complete isolation, leading to faster, more reliable, and more comprehensive test suites. Framework and technology independence. By design, these architectures ensure that your crucial business logic is not locked into a specific framework or technology. This means you can swap out your database, UI framework, or even switch from a monolithic application to a microservice with significantly less effort and risk. Enabling change and maintainability. The clear separation of concerns and the directed flow of dependencies make these systems inherently more maintainable and adaptable. Changes in one area, e.g., a new UI, typically don't cascade through unrelated parts of the system, allowing for more agile development and longer system lifespans. The subtle distinctions, unveiling the nuances. While the common ground is vast, there are conceptual differences and different points of emphasis that distinguish these architectures. Metaphor and emphasis. Hexagonal architecture, ports and adapters. Its primary metaphor is the hexagon, the core, interacting with the outside world via ports, interfaces and adapters, implementations. Its strength lies in explicitly defining interaction boundaries for external systems. It excels at showing how external actors interact with the core. It is less prescriptive about the internal structure within the hexagon itself. Onion architecture, concentric layers. Its metaphor is the onion, emphasizing concentric layering with the domain model at the very center. It strongly emphasizes the type of layers, domain model, domain services, application services, infrastructure, and their strict inward dependencies. It's more about the systematic stratification of concerns, particularly inside the application boundary. Clean architecture, unified vision. This is a meta-architecture, a synthesis. It takes the best ideas from layered architectures, like onion and portend adapter approaches, like hexagonal, and generalizes them into a set of principles and a specific four-circle structure, entities, use cases, interface adapters, frameworks, and drivers. Its strength is its comprehensiveness and rigid enforcement of the dependency rule across these distinct responsibility levels. Level of prescription and detail. Hexagonal. Relatively less prescriptive about the internal layout of the core. While it defines ports, it doesn't strictly dictate how the business logic within the hexagon should be organized, e.g., whether you use entities, services, etc. It leaves more room for interpretation of the internal structure. Onion, more prescriptive about the internal layers. It explicitly defines the domain model, domain services, and application services layers, guiding how business logic and use cases should be organized within the core and how they relate through abstractions. Clean, the most prescriptive. It outlines 4 distinct circles with clear responsibilities, entities for enterprise-wide business rules, use cases for application-specific business rules, interface adapters for translating data to and from outer concerns, frameworks and drivers for the concrete external details. This framework provides a more detailed roadmap for structuring code within the isolated core and at its boundaries. Distinction of business rules. Clean architecture explicitly differentiates between 2 types of business rules. Enterprise business rules, entities, which are highest level and unlikely to change, and application business rules, use cases, which are specific to the current application and detail how data flows and rules are applied for specific use cases. While hexagonal and onion implicitly contain these, clean architecture makes this distinction a core part of its layering, placing entities at the absolute core and use cases just outside them. This allows for an even finer grain of stability and reusability. Are they the same? No, but they are cousins. To directly answer the common question, no, they are not exactly the same. However, they are all direct descendants of the same architectural philosophy, particularly the separation of concerns and the dependency inversion principle. Hexagonal Architecture, 2005, pioneered the idea of isolating the core domain through ports and adapters, focusing on the boundaries of interaction. Onion Architecture, 2008, built upon hexagonal's principles but placed a stronger emphasis on layered structure within the application, explicitly naming concentric layers and strictly enforcing inward dependencies. It refined the internal organization. Clean Architecture, 2012, synthesized the core ideas from hexagonal, onion, and other similar patterns, such as boundary control entity and screaming architecture, into a generalized, comprehensive, and highly prescriptive framework. Robert Martin explicitly acknowledges these prior works as influences, stating that clean architecture takes all these architectures and partitions them into a single testable entity. You could say that clean architecture is the generalized, formalized, and most encompassing version of the principles that hexagonal and onion also champion. An application designed with onion architecture will look very much like a clean architecture application, and vice versa. Similarly, an application structured with ports and adapters will fit neatly within the interface adapters and use case layers of a clean architecture system. Choosing an architecture, principles over patterns. Given their strong similarities, how do you choose? In practice, the choice is less about picking one strictly over the others and more about understanding the underlying principles and applying them consistently. If your team prefers a strong visual metaphor for boundaries and clear input-output points, hexagonal architecture might resonate well, especially when discussing external integrations. If you need a clear, structured way to organize your application's internal layers, with emphasis on the domain, onion architecture provides a straightforward approach. If you desire a comprehensive, highly disciplined, and opinionated framework that dictates where every piece of code should reside for maximum independence and testability, clean architecture offers the most detailed roadmap. Many developers find themselves implicitly creating a clean architecture when they try to genuinely apply hexagonal or onion principles rigorously. The specific distinctions often become academic when you prioritize the core concepts, protecting the business logic, inverting dependencies, and making your system testable and adaptable. The goal is not to perfectly replicate a specific diagram, but to internalize the philosophy. Your business rules are king, and they should be independent of changes in databases, UI, and external frameworks. How you name your layers or draw your circles is less important than consistently adhering to the dependency rule and separating concerns. With this comparative analysis complete, we now have a solid theoretical understanding of these architectures. The next step is to bridge the gap from theory to practice, exploring how to implement these concepts in real-world software development. Chapter 7, From Theory to Practice, Implementing Architectures. We've now journeyed through the theoretical landscapes of hexagonal, onion, and clean architectures, understanding their shared principles and subtle differences. But architectural patterns aren't just pretty diagrams, they are blueprints for building real-world software. This chapter bridges the gap between theory and practice, outlining common strategies and considerations for implementing these architectures in your projects. The transition from understanding the why to figuring out the how requires a shift in perspective. While the diagrams might show distinct circles or layers, in practice, these often translate to well-defined modules, folders, or projects within your development environment, interacting through carefully managed dependencies. The cornerstone, dependency injection (DI). If the dependency rule is the heart of these architectures, then dependency injection (DI) is the indispensable tool that makes it beat. DI is the practical mechanism that allows inner layers to define interfaces without knowing anything about their concrete implementations, which reside in the outer layers. Recall the example from Chapter 2. Your business logic might need a way to save a user. Instead of creating a specific database repository itself, it defines an iUser repository interface. Somewhere in an outer layer, a SQL user repository or Mongo user repository implements that interface. The magic of DI comes in at application startup or during object creation. A DI container, a specialized library or framework, is configured. You tell the container, whenever something asks for an iUser repository, give it an instance of SQL user repository. When your core business logic, e.g., a create user use case, is instantiated, the DI container recognizes its dependency on iUser repository and injects the preconfigured SQL user repository instance into it. This process ensures that your inner layers remain oblivious to the concrete technologies used for persistence, messaging, or any other external service. They operate purely on abstractions. Without DI, practically implementing the dependency rule on a large scale becomes incredibly cumbersome, often leading to manual dependency management that undoes the architectural benefits. Project structure. Laying out the folders. The concentric circles and layers are most often realized as distinct modules or projects within your development solution. While specific naming conventions can vary, a typical structure might look something like this, reflecting the inward-pointing dependencies. Core/domain project. Content contains your purest business logic, entities, value objects, and domain events. This is the innermost layer. Dependencies has no external dependencies of its own. It's completely independent. Application project. Content defines application-specific business rules and use cases. It contains interfaces, ports, for any external services it needs, such as iRepository interfaces for data access or iExternal service interfaces for third-party integrations. It also defines data structures, request-response models, or DTOs for input and output of use cases. Dependencies depends only on the core/domain project. Infrastructure project, content, contains the concrete implementations of the interfaces defined in the application project. This is where you find your SQL database repositories, ORM configurations, external API clients, logging frameworks, and specific web framework utility classes. Dependencies depends on the application project to implement its interfaces and potentially on various external libraries, e.g., database drivers, HTTP client libraries. Presentations/UI project. Content houses your user-facing components, such as web controllers, API endpoints, desktop UI forms, or mobile app screens. It's responsible for receiving external requests, translating them into appropriate calls to the application project, specifically the use cases and formatting results for the user. Dependencies depends on the application project and relevant web or UI frameworks. It will also indirectly use the infrastructure project via dependency injection. Tests projects, content, contains your unit, integration, and end-to-end tests structured to mirror your architectural layers. Composition root project optional but recommended. Content, a single, isolated location where the dependency injection container is configured. This is where all the different concrete implementations from the infrastructure project and the presentation project are wired up to satisfy the interfaces defined in the inner layers. This project typically has a dependency on all other projects, as it needs to know about every component it manages. This project structure directly mirrors the concentric circles and layers, making the adherence to the dependency rule explicit in your file system and build process. A compile time check can even enforce specific dependencies between projects, preventing outer layers from referencing inner ones. Interacting with the unruly outside world. One practical challenge is how data flows across these distinct layers, especially when your inner layers need to remain independent of external data models, e.g., database entities or API payloads. Input-output models, DTOs. It's common for use cases in the application layer to define their own specific input and output data transfer objects, DTOs or request-response models. For instance, a create user use case might accept a create user request object containing only the necessary fields for creation and return a user-created response object. The web controller, in the presentation layer, is then responsible for mapping the incoming HTTP request data to create user request and mapping user-created response to the outgoing HTTP response. This prevents your core logic from being coupled to web framework or database-specific data structures. Gateways repositories. When a use case, application layer, needs to store or retrieve data, it calls a method on an interface, e.g., iProduct repository. The actual implementation of this interface, e.g., SQL product repository in the infrastructure layer, is responsible for translating the clean domain objects into the format required by the database, e.g., an ORM entity, and performing the persistence operation. When retrieving data, it maps database-specific results back into pure domain objects or DTOs that the use case understands. Testing strategy in practice. These architectures fundamentally simplify testing, allowing you to build highly reliable systems. Unit tests for core domain and application. This is where you get the most leverage. Focus, testing your entity's domain models and use cases application services. Isolation. These tests run without any external dependencies. For any interfaces that the core application layer depends on, like iUser repository, you use mock or stub objects. These are lightweight, in-memory fake implementations that mimic the behavior of the real dependencies. This makes these tests incredibly fast and deterministic. Benefit. Ensures your business logic is correct and robust, independent of how it interacts with the outside world. Integration tests for infrastructure. Focus. Testing the concrete implementations of your iRepository or iExternal service interfaces. Environment. These tests typically require actual external dependencies, such as a real database or a simulated external service. They verify that your SQL user repository correctly interacts with your database, for example. Benefit. Ensures your adapters correctly translate between your application's clean interfaces and the external world's messy details. End-to-end, E2E, or system tests. Focus. Testing the entire application stack, from the UI down to the database and backup. Environment. Runs against a fully deployed application, often in a staging or test environment. Benefit. Provides confidence that all the pieces are wired up correctly and function together as expected. While slower, they confirm system integrity. By having strong unit tests on your core layers, you significantly reduce the need for extensive, slow E2E tests, allowing for faster feedback loops during development. Practical considerations and challenges. While the benefits are clear, implementing these architectures isn't without its challenges, particularly for teams new to the approach. Initial overhead. there's a certain amount of boilerplate code and setup required. Defining interfaces, structuring projects, and configuring DI takes time upfront. For very simple CRUD, create, read, update, delete applications with minimal business logic, this overhead might feel disproportionate to the benefits. Learning curve: team members need to deeply understand the principles, especially the dependency rule and dependency inversion. Resisting the urge to take shortcuts, like letting an inner layer depend on an outer one, requires discipline, tooling, and community support. While modern languages and frameworks increasingly support these patterns, knowing how to properly integrate your chosen architecture with your specific tooling, e.g., ORMs, web frameworks, is crucial. Maintaining purity: as applications evolve, there's always a temptation to let new features leak concerns across layers. Regular code reviews and architectural discussions are essential to maintain the integrity of the design. When to apply: these architectures shine in complex, business rule-heavy applications that are expected to have a long lifespan and undergo significant evolution. For a throwaway prototype or a very simple application, a more traditional layered approach might suffice, though understanding the principles still helps. Implementing clean, onion, or hexagonal architecture is an investment. It pays dividends in the long run by delivering systems that are more flexible, easier to test, and adaptable to change. It transforms your codebase from a tangled web into a robust, maintainable asset that can gracefully evolve with your business needs. Having explored both the theoretical underpinnings and practical implementation strategies, our journey is nearing its end. In the final chapter, we'll reflect on the overarching benefits of these architectural approaches, discuss remaining challenges, and consider their ongoing evolution in the ever-changing landscape of software development. Chapter 8. The Road Ahead: Benefits, Challenges, and Evolution. Our journey through hexagonal, onion, and clean architectures has revealed a profound and consistent philosophy. Safeguard your core business logic, isolate it from volatile external forces, and enforce strict dependency rules. We've seen how these patterns, while distinct in their metaphors and degrees of prescription, converge on the same fundamental goals. Now, as we draw this exploration to a close, let's reflect on the enduring benefits of these approaches, acknowledge their ongoing challenges, and consider their place in the ever-evolving landscape of software development. The rewards of disciplined design: a summary of benefits. Revisiting the chaotic, tangled web from our first chapter, it becomes clear that the architectural patterns we've explored offer powerful antidotes. The benefits of applying clean, onion, or hexagonal principles extend far beyond mere technical elegance. They directly impact business agility and long-term project viability. Exceptional testability: this is perhaps the most immediate and profound benefit. By isolating business logic from external frameworks, databases, and UI, you empower developers to write incredibly fast, reliable, and comprehensive unit tests. Bugs are caught earlier, development cycles are quicker, and team confidence soars. Unparalleled flexibility and adaptability: the core value proposition of these architectures is their ability to enable change. Whether it's swapping out a database technology, migrating to a new web framework, or redesigning the user interface, the impact on your precious business logic is minimal. This protects your investment in code that truly defines your unique offering. Enhanced maintainability and understandability: clear boundaries and explicit dependencies make the code base easier to navigate and understand. New team members can onboard faster, and developers spend less time untangling spaghetti code. This translates directly to increased team productivity and job satisfaction. Longer system lifespan: software built on a solid architectural foundation is inherently more resilient to the passage of time and technological shifts. Your core application logic becomes a durable asset, capable of outliving the numerous frameworks and tools that will come and go. Improved business agility: when the code base is easy to change and test, the business can respond more quickly to market demands, pivot strategies, and deliver new features with confidence. The architecture becomes an enabler of innovation, not a blocker. Reduced technical debt: while no architecture can eliminate technical debt entirely, These patterns significantly reduce the likelihood of accumulating the debilitating kind that arises from intertwined concerns and opaque dependencies. These are not just theoretical advantages. Companies across industries, from startups to large enterprises, have adopted these architectural styles to successfully build and maintain complex, mission-critical systems that adapt to continuous change. The ongoing journey, challenges, and considerations. Despite their profound benefits, implementing and sustaining these architectures comes with its own set of challenges, some of which require ongoing discipline, initial learning curve, and buy-in. For teams accustomed to more traditional, simpler layered architectures, or even no architecture at all, the concepts of dependency inversion, ports and adapters, and distinct use cases can be a significant mental leap. Investing in education and demonstrating the long-term benefits are crucial for successful adoption. Perceived overhead for simple projects. Critics sometimes argue that these architectures are over-engineering for small, short-lived, or purely CRUD-based applications. While it's true there's an initial setup cost in terms of project structure and boilerplate code, it's a careful balance. Even for simpler applications, understanding the principles can guide better design, even if the full pattern isn't strictly implemented. The line between simple today and complex tomorrow is often blurry. Maintaining purity, the temptation to take shortcuts, to let an inner layer accidentally depend on an outer one, or to mix concerns, is a constant battle. This requires discipline, rigorous code reviews, automated architectural checks, and a strong cultural commitment to the chosen design. The last-mile integration. While they strive for framework independence, at some point, your application will integrate with a specific web framework, database, or UI library. Configuring dependency injection, mapping data models between layers, and handling framework-specific conventions can still be complex, even if the core remains clean. These are not insurmountable obstacles, but rather aspects that require conscious effort, ongoing team communication, and a commitment to architectural discipline. The evolution. Adapting to new paradigms. The core principles behind hexagonal, onion, and clean architectures were articulated decades ago, or in the early 2000s. Yet they remain remarkably relevant in today's rapidly evolving software landscape. Why? Because they address fundamental problems of software complexity and change, problems that persist regardless of the underlying technology. Microservices. These architectures lend themselves perfectly to microservice design. Each microservice can itself be built using clean architecture, ensuring its internal boundaries are strong, its business logic is pure, and it can be independently deployed and scaled. The emphasis on independent, testable components aligns seamlessly with the philosophy of small, autonomous services. Serverless computing. Even in a serverless environment, where individual functions might be small, applying these principles ensures that your core logic within that function is still decoupled from the triggering mechanism or the persistence layer. Testability remains paramount. Event-driven architectures. These architectures thrive on loose coupling, a principle deeply embedded in clean, onion, and hexagonal designs. Your domain's reaction to an event can be a use case, triggered by an interface adapter, e.g., a message queue listener, and then persisting changes via a repository, all while the core remains event platform agnostic. Reactive programming and functional architectures. While the implementation details might differ, e.g., using streams and immutable data structures, the goal of separating concerns, isolating side effects, and creating testable units of business logic remains fully supported by these architectural philosophies. The enduring power of these architectures lies in their focus on principles over patterns and on business value over technological trends. While the tools and platforms we use will continue to change, the challenge of managing complexity, enabling change, and building resilient software will always remain. Your architectural journey. This book has provided you with a robust framework for approaching software design. You now understand the underlying motivations, the core principles, and the specific patterns of clean, onion, and hexagonal architectures. Armed with this knowledge, you are better equipped to ask the right questions, Instead of focusing on which framework to use, you can now focus on how to protect your business logic from that framework. Make informed decisions. You can analyze trade-offs, understanding the long-term implications of architectural choices. Build future-proof systems. You can design software that can adapt, evolve, and remain a valuable asset for years to come. Remember, architecture is not static. It's a living, breathing aspect of your software that requires continuous attention, refinement, and adaptation. The practices we've discussed provide a powerful starting point, a way to untangle the codebase and ensure that your software not only fulfills its present purpose, but is also ready for the road ahead. Embrace the discipline, champion the principles, and build software that truly lasts.